divided by the square root of 100 squared plus 150 squared minus 200 squared, then divided by 3. Although it is not exact formula because we are using rounding average and assign a different weight, some different principles. But yeah, this is rough idea. So that if the previous gradient magnitude were really large, and then we just scale it down properly. At the same time, for these guys, it will not be scaled to that much. So that way, we want to make approximately the same amount of gradient, or same gradient magnitude across different domains. So that's the idea of this RMS plot. Okay, so that way we accumulate this gradient squared, and then with the running average, and then divide it. Yeah, dimension number. Okay, add-on is the combination of this RMS plot and momentum. Instead of just using gradient, we basically put this momentum, which works as the gradient effect and obtain this x. So yeah, overall this is probably one of the most frequently used optimizer in practical in architecture. Then yeah, we discussed about this tricky issue about this bias correction stuff. Okay, then the one thing that I wanted to show last time was this guy. It's just 631 action notes. So here, so this is a saddle point example. So given this saddle point, the gradient plus all the different dimensions will almost be 0. Right? But if we have the momentum vector, and then even though the gradient magnitude is really small at the particular time step, if it was accumulated with the same sign, then the current time step it will have some non-trivial amount of gradient. So it's easy to escape from this settlement. And also in this case it's a much complex landscape of our function. So here, intuitively the color gets more blue, and then it's a lower function value. Right? So we want to arrive this value, which is the lowest height. Okay, so in this case, you can see different behaviors of different algorithms, and you see stochastic gradient set as red, and the momentum, and the lesser momentum, and the eta gradient, and the RMS plot, and also we haven't studied this eta RMS plot, but we will skip this explanation. Anyways, we can see some interesting aspects. Right? In the case of momentum, it will overshoot a lot. So around this region, even though it is an uphill because of the accumulated gradient, it will still go up. Right? But eventually, it will go down to the this local minimum. Okay, and yeah, overall, among these, RMS part and eta delta seem to work well. But if you use an add-on here, then you will work as good as those algorithms, or sometimes it's even better. In terms of convergence speed, okay, also it's giving a better quality of the local minimum, which means that the converging points, we may have a smaller loss value using add-on compared to other MSs. Okay. order and the second order optimization. So it is related to this scalar expansion. So the scalar expansion is to approximate this complicated functions as a simple first order or the second order degree polynomial. Like given this complex functions of we can approximate it as ax plus b, or as a second order polynomials, and then we can just approximate it in these two forms. So in order to approximate this given complex function, this singular function, we have to first fix or particular point. That's usually how this scalar approximation works. So for example, we specify a particular point. Then how we approximate this complicated function into this form is by making the first and the zeros order, the first order derivative the same between the two graphs. Okay? So in this case, suppose we just approximated this complex graph as a single line. Okay? In that case, it means suppose this function is this approximate this function as g, or g is these are approximate. Okay, then first this is a single point. This is a zero order equation. And the first order equation is which makes the first derivative. So first order derivative to be the same between the two graphs. So especially when this is a particular point x. So again, we start with the particular point x comma y. So we find out this a and b by just setting this guy two equations. By satisfying these two equations, we found a and b. This is the first order approximation, and this is basically what lies is scalar expansion. But we can, in the case of the scalar expansion, it is related to gradient descent. At this particular point, if we approximate the whole function to get lower in terms of a function value will be like this direction, right? So that is the intuition used in the gradient descent. But in the case of second order optimization, we basically approximate this as the second order polynomial, and we basically add another constraint or another equation like this. Okay, and so in this case, the function value itself should match, and the first order derivative, which means the slope, should match, and also the degree of this increase or the acceleration or this second order derivative should also match, right? So in that case, at this particular point, we can suppose that approximated graph is represented as this blue line. Okay, in this case, because we assume that the entire graph is just like that, and so in the case of this this is a second order curve, and then we can directly compute the minimum possible point. I mean the minimum point in terms of the function value. Okay, so if we just approximated this graph as 2x squared plus 3x and minus 5, and then the minimum point will be easily computed as negative 3 over 4, right? And so even though we started from a single particular point,
once we approximate it as a second order derivative, second order polynomial, and then we can just go directly to the minimum possible point based on this second order polynomial assumption. Okay, and then this will be the next point in our iterative optimization. And then at this point we evaluate our function value. Okay, so we basically moved from here to here, and then our function is over here, and then our second order approximation will be something like this, right? To match the function value itself and first and the second order derivative, and then the minimum point will be somewhere around here, right? So we jump to that point directly. So in terms of the difference between this first order and the second order optimization, I mean the first order optimization is a gradient descent, and the second order works in this manner. And the main difference is that we don't need any step size in the second order optimization, right? Because we can just directly go to the minimum possible point from this second order approximation. But to obtain this second order polynomial as our approximation, it actually involves the second order derivative of our given function. So at this point, what we did was to have the function value itself, and then we computed the gradient, which is the first order derivative with respect to individual variable that we have, right? So if our parameter, the number of parameters are 10, and then what is the first order derivative or the gradient vector dimension? It will be 10 dimensional vector, right? And then we can, how about the second order derivative? So our function itself is a scalar, and we can consider is x1 through x10, right? Okay, and then that's how we obtain 10 different gradients with respect to individual variable. But in the case of second order derivative, we can actually, so this could be one possible second order derivative, and maybe 2 and 3 and so on. So that way we may think of like 10 different second order derivative, but actually, in fact, we can think of many other second order derivatives. Like, we first take the derivative with respect to x1, and then given this function, we also compute its partial derivative with respect to x2. So those two values can vary from 1 to 10, and so the second order derivative is resulting in, so it's a 10 dimensional vector, and the second order derivative, which is called the Hessian matrix, is having the size of 10 by 10 matrix. Okay, and somehow we actually need to compute its inverse matrix. Okay, so computing the inverse matrix requires the computational complexity of 10 to the power of 10 cubed. Okay, so that way it's involving a lot of computation, and also even if we follow this second order derivative, we basically have to maintain this much this much size of the matrix, right? So it's quadratic in terms of the number of parameters, and as you saw in the VGGNet or ResNet and so on, the total number of parameters can be more than 1 million. So we can somehow manage the million number of parameters within our GPU or our computers, but the square root of these numbers cannot be manageable. Okay, so that way in practice this second order optimization is not used much. Okay, any questions about this? 네. 지난번보다 잘 안 들려요? 이 마이크를 여기 올려놓으면 뭐가 이게 펜을 쓰는 소리까지 가갖고 내가 그랬는데 지금 잘 들려? 네. Any other questions other than increasing voice? Okay, and yeah, there are many different second-order optimization methods, and this BFGS or LBFGS, which reduces the required size, memory size. Yeah, this LBFGS is the most popular one. Yeah, but yeah, when training the neural net, as because the number of parameters is too large, so yeah, we don't use this second-order optimization much. Okay, and model ensembles and regularizations. So have you guys understand this? Right? So it's like, so starting from here, yeah, suppose we arrived at this point, which is like a little bit flat region, but the gradient is not completely zero, right? So in this case, yeah, the gradient became close to zero, and thus we don't have a momentum. Yeah, we don't actually have the enough force to escape out of that point, right? And so if our loss function plateaus, and then yeah, sometimes we actually decrease the learning rate to actually to actually go to really fine point. Okay, really so it's like, so if we have this loss function, and then starting from here, and then suppose we arrived at this point, and then we have some gradient, and then if we use still the learning rate that we used in the previous iterations, and then it might be too high to reach at this exact local minima or our global optimal point, right? So in this case, it may be like a bouncing around, okay? Because our learning rate is too high to reach at this exact point. So in that case, we sometimes reduce the learning rate, okay? So that is one strategy. But what if the current point is like a saddle point where we still have some direction to go down, but at the current position, it is almost flat. So in that case, we can actually, boost up our learning rate as a bigger ones, and then that can help to escape from a saddle point. Okay, so this is one kind of a strategy to adaptively change our learning rate. And let me show another strategy. So I'm not sure if we can cover this transformer model, but at least we will cover the notion of the self-attention, which is really exciting and interesting kind of technique, which brought a lot of performance improvement in many different applications. And so this transformer is widely used, especially in the natural language domain. Okay. So in this transformer, it actually has used a different learning rate, adaptive changes of learning rate. So what they used is like this. So we start from really small learning rate. So this is the learning rate graph, and then x value is the iteration index. So as we go on, we gradually increase the learning rate. So that means, why do we use a small learning rate at first or at the initial stage? Because we start from really at the random point, right? And at the random point, our gradient might, the magnitude of our gradient might be sufficiently large, right? So at that moment, if we use the high learning rate, and then it can diverge, right? So for example, in this simple case, suppose we started from here, and the gradient is large, and the learning rate is large, and then it can move this guy to over here, and then the gradient became even larger, right? And if we use the same step size, and then it will just jump it to another point. So it's actually making this our point diverge out of this global or our optimal point. So that way we basically use a small learning rate at first, and then if the gradient gets smaller and smaller, and then in order to give a more kind of momentum, more force, we use a higher learning rate. Okay, and then now we start to decay or decrease the learning rate, because it is assuming that we arrived at this region where the global optimum can be found by really fine-tuning that point, right? So that way we reduce the learning rate. Okay, so this is called the warm-up scheduler of our learning rate. So this is another kind of trick that this method has used. Okay, I believe you guys have understood the main idea of the dropout. And the main idea of dropout is that we don't want to rely on only some small portion of the information, right? So if we want to recognize a cat, and then we want to kind of aggregate all the information that are given to us, instead of just relying on a single particular information. So suppose in our training data, cat image all has the ear, for example, and then this cat will have a lot of other characteristics or other features that will distinguish cat from other objects, right? But still, if our training image has all the ears for this cat images, and then it has no problems to rely only on this information of whether we have a ear or not, right? So in that case, what if our test data gives a cat image that doesn't have an ear due to like a cropped image, and then it will have no way to recognize it as cat, right? So that way we intentionally and randomly drop out this information, right? So that is the main idea of this dropout. So that will generally help to improve the performance of unseen data, right? So that way it can be viewed as a regularization method. Okay, and also it can be viewed as the ensembling many different models within a single training or single model. And have you understood this part? How we adjust the test, our neural net output in the testing phase? So suppose this output takes the 3 input node, maybe X, Y, Z, and during the training time, they are randomly dropped out with the 30% of the probability. So overall, this node will be present with the 70% probability, and the other 30% probability, it will be dropped out, right? And so they will be added anyways with some weight values assigned to each of them, and then if they are dropped out with the ratio of the 70% probability, and then the usual magnitude or usual amount that is collected at this node will be just 70% of the magnitude computed from all the nodes, right? So in the case of training time, we randomly drop or remove them with some probability, but during the test time, we use the full capability of our trained network. So we don't actually drop out any node during the test time, right? So in that case, this will have an unintentional effect that the magnitude that is received by this node is increased, right? what is the ratio of this increase? Because we dropped out with the 30% probability, or we made them alive with the 70% of the probability, and when using all of them, and then we will have like 0.7, like 1 over 0.7 ratio. I mean, that is the ratio of this increase of the received output, right? So that will mess up our batch normalization, or the ideal range that is given to, ideal range of the input that is given to our nonlinear units and so on, right? So maintaining the same range of the input or activation values, it is really important. So in order to like adjust this aspect, we actually scale this down by 0.7, right? Okay, so so that is reflected in this code, right? So we don't actually do the dropout during the test phase, but so we actually scale down this output, just like the case where we drop the node with the 30% probability. Okay, so this is one additional code that we have to add in the testing time when using the dropout. And also, you guys understand this inverted dropout, right? So in the case of an inverted dropout, the main idea is that so this additional multiplication with the p will actually make our testing time computing time during the test phase slower, right? Because it is introducing additional computation, right? So we want to make the testing time as fast as just the case without any dropout, right? So we don't, we actually want to remove this guy, right? And then how can we do that? So we maintain the exact same test code like that, which ignores this effect of the dropout, but we actually adjust during the training time. And how? So if we did so in this case, we apply suppose we apply the dropout with the 70% probability of making them alive, and then given this output during our training time, we actually increase it by 1 over 0.7. Okay, so we basically increase the magnitude of our activation, as the level where we obtain when using the full node without any dropout, right? So okay, so that is this guy, right? So we basically increase the number of, increase each of this activation values, right, while doing the dropout during the training stage. Any questions so far? 네. 네. 그렇죠. 네, 그런데 베리언스가 작아지죠. 근데 이제 배치놈은 그 작아진 베리언스를 기준으로 얘를 노멀라이즈를 하겠죠. 그렇죠? 네. 그러니까 어쨌건 우리의 배치놈, 뒤에서 후처리로 쓰이는 배치놈이든 앞쪽에서 쓰이는 우리의 웨이트든 어찌됐건 얘는 얘대로 이 드롭아웃, 그러니까 10개 중에 3개가 버려지는 상황에서 어떤 최적의 레인지가 되도록 뭔가 이 웨이트가 알아서 키워지거나 아니면 배치놈이 알아서 그걸 뭔가 키워주거나 할 건데, 네. 근데 중요한 거는 트레이닝 할 때는 어쨌건 이게 엔드 투 엔드로 뭔가 되기 때문에 이거는 그냥 알아서 다 되는 거고, 우린 드롭아웃을 적용을 해주기만 하면 되는데, 이제 테스트 타임에서는 드롭아웃을 결론적으로 안 쓰니까. 왜 안 쓰냐? 우리는 뭔가 정보를 빼먹고서는, 그러니까 뭔가 정보를 빼뜨려갖고 학습 때 뭔가 더 하드하게 트레이닝 할 수는 있지만, 이제 테스트에서는 우리의 풀 퍼포먼스를 내야 되기 때문에, 뭐 노드를 이제 뭐 있는 정보를 막 이렇게 막 버리는 게, 없애는 게 이거는 우리가 원하지는 않는 거라는 거죠. 그래서 이제 모든 노드를 다 썼을 때는 거꾸로 이제 그 베리언스가 커지기 때문에 그만큼은 이제 줄여줘. Any other questions? Okay, so that is the dropout. And so, yeah, batch norm and dropout can both be viewed as the regularization techniques. And yeah, some student asked the question about whether we use both of them, or sometimes do we use one of them or not at all. So usually we use the batch norm first, and usually batch norm will work as a sufficient regularizer. So in practice, we don't actually use batch norm and dropout, both or simultaneously. Okay, but between the two, I think, to my understanding or to my knowledge, the batch norm is the first that we add as our regularizer. Okay. And also, we can do a lot of data augmentation, and actually this step will work really as an important step to improve your performances. Okay, so in practice, we always don't have enough number of the data. So we don't just handle the problem where the enough data is provided. Our problem is a quite new problem, and so we want to solve the new problem based on our own collected data, and in many cases the number of data is really small, and so in that case this data augmentation will work as really effective method to improve the performance of an unseen data. So any questions about, so you guys understand this? So this is another kind of randomization, right? So it's like, instead of just the max pooling over this regular grids like this, sometimes we increase or decrease some specific positions window when doing the max pooling. Okay, so that will also give us some randomization during our training time, and which will work also as a regularizer. But I'm not sure if it is widely used, but I think it's an interesting idea. Okay, we will actually have an opportunity in the later classes to discuss about this transfer learning, which is a really important concept. And I think, that's it for Chapter 7. Any questions about this Chapter 7? Okay, then regarding Chapter 9 about deep learning software, I actually don't have much background myself, because I haven't done any deep learning programming or coding myself. All my research about this deep learning is programmed or implemented by my students or other collaborators. So I just do the writing and giving some idea or directions. But anyway, so I actually don't have much background or insights to teach. I mean, enough background to teach about these. But but at a high level or in principle, among the many softwares, you guys have to understand carefully about the difference between static and dynamic graph. Okay. There was a slide, right? So one convenient thing when using this deep learning library is that most of them will provide the backpropagation function. So once we define our forward propagation, and then the formula for our backpropagation is automatically given or automatically computed by our deep learning software. So that way, even though we studied a lot on the backpropagation, which is really important still, but when actually programming or when doing your homework, for example, you don't actually need to write your own backpropagation code, because that is done by these deep learning libraries. but still, I think, how this backpropagation works in detail is really, really important, because sometimes there are some layers that is not differentiable, for example. Yeah, so in that case, so for example, let me give a simple example. Instead of the sigmoid, the sigmoid function is looking like this, right? So it is differentiable. But what if we use this guy? So this will work just similarly as a sigmoid nonlinear activation. So if it is a zero, negative output, and then it will output zero, negative input, and then it will output as zero. And if it is a positive input, and then it will give us output as 1, right? So this is a discrete version of the sigmoid, right? So we have no problem of using this discrete version of the activation function, right? But the problem of it is that this guy is not differentiable. But I'm not sure if it's the correct way to describe the situation, because it is differentiable except for this point, right? So the only point that is not differentiable is at 0, right? Because what is the necessary condition to be differentiable? It is at least the condition that the function should be continuous. So if the function is not continuous at that particular point, and then we cannot obtain the derivative, right? But what about the other points except for this 0, right? So suppose we are given the input as 3, and then what is the gradient at this point? The gradient is 0 exactly, right? So it is differentiable, but it actually prevents our networks from being trained, right? Because when doing the backpropagation on this layer, and then whatever gradient of dy comes in from the upstream, our gradient to be multiplied with that upstream gradient will be always 0, right? So that kind of flat shape of our graph is always giving the 0 gradient. So that will give us the problem of not being able to train our network of the lower layer, okay? But there are some fancy tricks to actually compute the gradients, okay? So there are many interesting or advanced techniques that can also incorporate this discrete functions, and also still being able to perform the backpropagation, okay? Okay, so back to this static versus dynamic graph. So I think I encourage you to carefully review the CS231 and lectures, but the main idea is that at every iteration we basically create the connection from scratch, okay? So we can we basically define or assign or allocate the memory for our nodes, right? So one node and the other node, right? And then that is just assigning the memory allocation for our variable, whether it's a parameter or activation value or input or output activations. And then there are connections like, okay, after performing this function, and then that output should be given as an input to another function, and so on. This whole path of this computations is actually set up or created from scratch at every iteration of our gradient descent update. So that is the idea of this dynamic graph, right? So it seemed to be really like, it seemed to be a little inefficient, right? So in that sense, once we just set up this connections, or how this computational graph is connected exactly in advance, and then there exists some efficiency that we can kind of incorporate, but that also has some disadvantages, right? So what if our data, changes, and then our computational graph should also change, right? So for example, there was an example of like a if statement, right? So in that case, it is not a static graph. So depending on our input data, we have to really route differently this input to different node, right? So that is kind of notion of the output, the dynamic graph. And this dynamic graph is also becoming really critical in the recurrent neural network or long short-term memory or gated recurrent units that we will study right after the midterm exam. Okay, so in that case, like the coding or programming this RNNs using this static graph-based deep learning library such as TensorFlow is really becoming messy. Okay, so the code is really becoming large and getting kind of spaghetti kind of shaped code. And so in that case, the dynamic graph-based deep learning libraries is really useful for dealing with this RNNs and so on. But I will skip the details because I don't have much ideas or much more knowledge than this original lecture. Any questions so far? Okay, and then let's finish this chapter 8 and then move on to chapter 9. And the first thing that we will study is the VGGNet of this. So some student also asked the question about it. So the receptive field, let me just describe what the receptive field, and I brought some paper. So this is a kind of video prediction paper. So the task itself is not really relevant from our context, but I wanted to bring this figure. Okay, so let's just ignore about this frame t-1 and t, and let's assume that is our layer 1 and layer 2. And this is a kind of example of a convolution, right? So in order to produce one single output, so how many pixels do we look at? So center that here, and we are looking at like plus and minus 1 pixel kind of neighboring kind of pixels, right? So in this case, we call this situation as like the receptive field being 3 by 3, right? But what if we just stack another layers, right? Like this, okay? So so let's consider this 3 by 3 and 3 by 3 convolution, okay? So in this case, let's just use this guy. So what is the receptive field from, let's suppose this is an input image, okay? This is our input image. And then what is the receptive field or the size of the regions that is involved to compute this single activation map in the first and the second hidden layer, okay? So this one we'll look at this 3 by 3 in the previous layer input, previous layer output, right? And then now, what about this guy? This guy is, which regions does it look at in this input? So this guy is looking at this region, and this guy is looking at this region, and so on, right? So when considering this 3 by 3 convolution, this a single node is looking at 3 by 3 region, and also it is further increased in terms of the receptive field in the case of this input activation map or input image. What is the receptive field size? It is 5 by 5, okay? And then let's think of some other cases. How about like 5 by 5, two stacked convolution layers of using 5 by 5 filters. So in this case, 5 by 5. And what about here? Is it like 25 by 25? Would it be correct? Okay. So yeah, because there are not many pixels or dots over here, let's just increase the filter size as a 4 by 4. Okay, and then it will have this activation map. And then this guy will also look at the other regions, right? In the input image, and this guy will have this regions and so on. So it is not really like multiplication, right? It is really addition, right? So given the single pixel, because we can think of this mapping from, as I mentioned, we can think of this mapping as from this point into this point, and then if our window size was 1 by 1, and then our receptive field will just stay as the same, right, as 1 by 1. But if we use the 3 by 3 filters, and then it will give one more kind of pixels on the left, right, and up and down, right? And then this guy, when considering the single pixel mapping over here, and then how many additional pixels can we look at in the input layer? So if we use the 3 by 3, and then it will still give another one more pixels on the left, right? So one pixel left and another pixel left, right? So it is really linear, right? Linear kind of increase, right? So in the case of 5 by 5, so it is increasing like two more pixels on the left, and then also 2 more pixels on the left in the another layer, right? So in the case of 5 by 5 layers, what will be the input activation map? So 5 by 5, and then, so we know that, right? So this one is the receptive field corresponding to that activation map in the middle, and then it will give us 2 more pixels on the left, right, and up and down, right? And so the receptive field will be 7 by 7, right? So starting from the single pixel, if our convolution is like 2 pixels on the left, like in the case of 3 by 3 pixels, centered at the center position, is giving us a single additional pixels. And if we pass 2 layers and 2 additional pixels and so on, right? Okay, so you guys now understand clearly about this, the meaning of or the notion of this receptive field, right? Okay, and then now let's get back to here. So here the situation is we stacked 3 convolution layers where each convolution layer has the filter size is 3 by 3, right? And so what will be the receptive field size? So starting with the 1 pixel, right? And then left and right, it will give us 2 more pixels in the first convolution and another 2 more pixels in the next convolution. So we are going backward, right? And then 2 more pixels, right, in the very first layer. And thus the receptive field is 7 by 7. So does it make sense? Okay, so so here in the case of an input image, when stacking 3 layers of 3 by 3 convolution layer, and then at the end each pixel is looking at or involving 7 by 7 kind of a large kind of sized window, right, in the input activation. Okay, so in that case, let's just consider another case where we only just have a single convolution layer. Okay, so instead of stacking 3 convolution layers, let's just use a single convolution layer that has the same receptive field. So in that case, we will just use 7 by 7 window or filter as our convolution in our convolution layer when using the single convolution layer to match the receptive field. Okay, so we want to be able to match the receptive field size. Okay, so that's the initial assumption. Okay. Okay, and then now in this particular case, we are considering this situation where we have width and height width and height, and some channel number C. I mean the number of channels in an input activation map is C. Okay, and then let's suppose we want to have another activation map that still has the same channel size as C. Okay, so in this case, let's just compute the number of parameters when just applying the single layer convolution that has the receptive field size as 7 by 7. Okay, and in this case, how many number of parameters do we need? So one filter will have this width and height, and because the input activation map is C, and so this is the number of parameters required for one single convolution filter, right? And we have to generate the C different channels, and thus we need C filters, right? And so it's 7 squared C squared is the total number of parameters needed to have a single convolution layer that has the 7 by 7 receptive field. Okay, and then now, so this is the first situation, and the second situation is, so we stack 3 layers, right? 3 stack layers, stack 3 layers, and the input is like this size, and output has this size, and we have a freedom to change our channels in the intermediate layers, but let's just assume that this guy is C, and the next activation map also has C, and also has C and C. Okay, so we consider this situation of stacking 3 layers of having 3 by 3 convolution. Okay, and then in this first layer, how many number of parameters do we need? So 3 by 3 is our filter size, and so this is an input and this is an output, right? Okay, so overall this is a 3 squared C squared, and we need 3 different layers, right? And so we need 3 sets of this much number of parameters, right? And so overall 3 times 3 squared C squared. So if we compare between these two numbers, so this guy is 27 and this guy is 49. So we can see that the first scenario requires much more number of parameters than the second scenario, right? So here again, the assumption is that we want to maintain the same receptive field size. Okay. Okay, so stacking this more number of layers while using really small filter size, so that will give us the smaller number of parameters required to have relatively large receptive field size. Okay, in terms of an input activation map, and at the same time, if we stack these 3 layers, the nonlinear units such as ReLU is introduced at 3 different places. But on the other hand, in the case of a single layer, we have only one chance of adding nonlinear units, right? So we have 3 different places that we can add or inject some nonlinearity, and thus in general it is better, okay, adding this nonlinearity more. Okay. So this is the main kind of idea or kind of intent of kind of design kind of rationale or kind of motivation of VGG nets. Okay, so in the VGG net, we only use the smallest possible filter size of 3 by 3, right, to take into account the nearby or spatial kind of patterns. Okay. So any questions? And then now, there was a question about in the Slido. I saw the question about why this nonlinearity is giving the good or better kind of a capability in our neural net, right? So so did I mention about this block posted by this Chris Ola. So he's a researcher working at a Google Brain. But interestingly, he doesn't have any, as I know, he doesn't have any degrees. I mean, higher educational degree such as master's or PhD. So he just graduated as an undergrad and then just directly joined Google at this Google Brain. Anyways, so in his blog, there are many interesting kind of blog articles that allows you to understand the complicated notions involved in the deep learning much easily. Okay, so here there are many different articles that you can read. I actually strongly encourage you to check each post in this blog, and in one of them is showing this simple example. So suppose this is our data in the context of a binary classification. So, for example, so let's imagine this x and y axis. So this is our feature space, and this is a weight, and maybe this is a height. Okay, and this line is not a kind of a regression line, but it's actually like when given this feature vector, this one has the positive label, and also this one also positive label, and this one has the negative label, and so on. So in this case, when using the linear classifier, such as logistic regression or support vector machines, there is no way to properly classify them because using any single straight line, so we cannot properly separate them into two separate regions, right? Okay, so this is the example. So probably this horizontal line might be the best one that has the smallest misclassification rate, right? Okay, so in the case of a linear and a nonlinear unit, I mean when using a neural net that has this nonlinear transformation in the middle, so that is actually transforming some regions, like they are squashing some regions into this form, right? So let's show, let's see the animation. So it seems to be quite slow. Yep, so it is getting squashed at a certain region, right? So that region is corresponding to the region squashed by our sigmoid function or this nonlinear transformation, right? So why do we say this word squashing? So in the case of, I think I described in this manner or not, but let's just consider the 10H, which is almost the same as this guy, but having a, so this is a 10H, and then if we don't use the any nonlinear units, and then let's just replace that nonlinear unit of this 10hx as just y equals x, okay, and then it will correspond to this this line, right? This is y equals x line. So given this input, the output should be here in case of no kind of no transformation or no distortion, but this meant this much value is actually squashed into much smaller value, and that amount of a degree of the squashing gets larger and larger as we get farther and farther from the origin, right? So that way, like that region is squashed much more, right? And so that is the effect that we see, like at the extreme regions at that corner. Okay. So after squashing these regions selectively or with the different degrees, and then starting from this, this is almost the same as the sinusoidal one that we saw. So let's look at the starting situation. So this is the the binary classification feature kind of vectors. And then we somehow linearly transform them and then squash some part. Okay? And then even though it gets smaller and smaller into like a little bit packed region, yeah, it is packed with the smaller regions, but within that smaller region, okay, at that point, okay, suppose we want to build a linear classifier that perfectly separates them, okay? So we can, do the job at that part. So if we would squash it like this, and then we can still form this nicely kind of linearly separable line in that, given that kind of a warped or squashed feature space, right? So that is the effect of the nonlinearity. Okay. Okay, so in general, nonlinearity will squash or distort some necessary part selectively, okay, so that we can provide better separable feature representation to the next layer, okay. So that is also represented or also shown in this example. So this is like a multi-class classification case. So have you studied about principal component analysis or multi-dimensional scaling, or even T distributed stochastic neighbor embedding? Okay, and then there is a machine learning technique called a dimension reduction. Okay, so dimension reduction is that suppose we have 100 data items where each data item is represented as like 4-dimensional feature vector, like weight, height, and blood type, and his location of residence, and so on. And then, so we have 100 different vectors in the 4-dimensional space, and then dimension reduction will actually reduce the dimensionality of each 4-dimensional vector into, for example, 2-dimensional vector. Okay, and then how do we do this dimension reduction? And what is the objective in this process? Typically the objective is to preserve their pairwise distance. So for example, okay, in terms of the feature representation, in terms of weight and height and blood type, for example, and if the two persons were having the similar feature representation, having similar weight and similar height and the same blood type, for example, and then their corresponding dimension reduced vector in 2-dimensional space, their distance should also be small. So they should be placed within the similar region. So that is the main idea of this dimension reduction. And one of the widely used dimension reduction algorithm is called, I personally like the name, and also I also do much research on this topic itself. Okay, why it is showing up, but let me just continue this explanation. So this is the example of dimension reduction result of the MNIST data. So you guys know the MNIST data. So MNIST data is 28 by 28 kind of grayscale picture representing a particular digits. And then once we represent it as a single vector, and then the total input dimension is 784, which is a 28 by 28 times 28. And then we suppose we have 100 different digit examples or digit images, and then we apply the dimension reduction to maximally preserve their pairwise distances if they were close in the 784 dimensional space, and then we place them closely in the 2-dimensional space if they are really far apart in the 784 dimensional space, and then we also put them far apart in the 2-dimensional space. And then we basically once we determine their 2-dimensional positions like this, so if it was 3 by 1, and then we can actually put their point, we can visualize them in this 2D, something called 2D scatter plot. So this is a dimension reduction result in two-dimensional space of some particular digit image. And then that digit image may have a different digit labels ranging from 0 to 9, right? And then this color indicates that digit label, right? Yeah, so I wanted to show the MNIST digit example, I mean TSNE visualization example, but yeah, Korea Univ AP doesn't allow me to do so. But anyways, yeah, so you get the idea, right? So the main idea or the main point that I want to make over here is that by using the 784 input dimensional representations, and then so roughly we have maybe several hundreds or several thousands of data points, and their colors are represented in terms of their digit labels, and thus roughly suppose this guy is a 0, and then 0 is roughly placed over here, and then many other classes are placed somewhere around in this 2D scalar plot. But yeah, we can see many overlaps between different digits, right? But once we do the once we go one layer further in our neural nets, and then this neural net, if our so in the case of MNIST digit example, input node will be composed of this 784 nodes, and then suppose we added the fully connected layer, and then we have the 100 node, right? And then for each input image, and then it will be represented as 784 dimensional vectors, and then once we transform them by using the first layer, and then that will be transformed into a 100 dimensional vector, right? And then we collect those 100 dimensional vectors for each of these data items, and then we redraw or we reapplied the dimension reduction, and this is the result. And so here we can see that different classes are better separated, right? Because in this input 784 dimensional space, and then it would be really difficult to classify between different classes because they are overlapping significantly. But once we get the one layer further, then those representations will give us more easily separable kind of a data representation or feature representation. Okay.
그룹이 같은 거를 만약에 숫자 데이터라고 하면 같이 8이라는 숫자를 대표한다고 가정한다고 해도 두 개로 나누는 문제가 발생하죠.
네. 그러니까 이 TSN이나 이런 디멘전 리덕션 메소드는 애초에 그 클래스 레이블이 뭔지는 전혀 상관을 하지 않고 그 해당 데이터 아이템이 뭐 100개가 주어져 있다. 그럼 100개에 대한 페어와이즈 디스턴스가 총 몇 개가 있죠? 100 곱하기 99 나누기 2개가 있잖아요. 언오더드 된 페어에 대해서 모든 페어와이즈 디스턴스를 오리지널 784 디멘전 스페이스에서 계산을 하면 그만큼 많은 페어와이즈 디스턴스가 있죠. 어쨌건 그 디스턴스를 우리는 입력을 해갖고 이 2D 상에서 얘네들을 잘 흩뿌려서 그들의 2D에서의 그 해당 디스턴스가 저쪽 오리지널 하이 디멘전 스페이스에서 멀었으면 이쪽도 멀게, 저쪽에서 가까웠으면 이쪽도 가깝게 하는 거지. 거기서 이제 그 클래스 이 과정 중에는 이 어떤 데이터가 누가 1이었고 누가 이제 뭐 0이었고 누구는 그래서 같은 클래스고 누구는 다른 클래스인지는 전혀 상관하지 않잖아요. 네. 그랬는데 이제 뭔가 해봤더니 이게 대충 보니까 여기서도 보면 인풋에서 이렇게 해봤더니 이제 같은 클래스에 해당하는 데이터 아이템들이 그래도 한 곳에 모이더라. 네. 그러니까 뭔가 우리 데이터가 이제 클래스가 그래도 우리가 처음에 만든 이 784 디멘전으로 볼 때 이걸 기준으로 했을 때는 그래도 어느 정도 이렇게 분리가 가능한 형태다라고 우리가 이해를 해볼 수가 있고요. 근데 이제 또 우리가 레이블을 설정하는 과정은 이 피처 벡터랑은 완전히 다르잖아요. 그러니까 똑같은 피처 벡터에 대해서 그러니까 키, 몸무게, 혈액형에 대해서 우리가 레이블을 뭐 이 사람이 남자냐 여자냐를 줬을 때랑 그 다음엔 이 사람이 뭐 연봉이 1억이 넘느냐 아니냐를 했을 때랑 네, 그 레이블만 다르게 줄 수 있잖아요. 같은 피처들에 대해서. 그럼 결국 이 2D 플랫은 변하지 않겠죠. 여기에 어사인되는 컬러만 바뀌겠죠. 그쵸? 왜냐하면 이 2D 디멘전 리덕션은 그 페어와이즈 디스턴스, 그 걔네들이 할당된 추가적인 그 레이블은 전혀 고려를 안 하니까. 네. 그래서 어떨 때는 이제 2D 임베딩을 해놓고 거기에 우리가 추가적으로 우리가 별도의 프로세스를 통해서 별도의 정보를 통해서 레이블을 할당을 했고 그거를 여기 이렇게 컬러로 입혀주면 그게 뭔가 클래스별로 잘 모여진 형태로 나타날 때도 있고 같은 데이터에 대해서 이제 좀 다른 레이블을 할당을 하면 그게 막 서로 섞여 있을 수도 있고 아까 얘기했던 것처럼 같은 클래스인 것 같아 보이는데 이게 여기랑 저기에 이렇게 두 가지 무리로 나타나기도 하고 그래요. 그거는 이제 우리 데이터가 실제로 우리가 부가적으로 준 이 별도의 이제 레이블링을 할당하는 그 프로세스라고 할까요? 그거랑 그런 식으로 뭔가 미스매치가 있다는 거죠. 답이 됐나요? 지금? 다른 혹시 질문 있어요? 코리아의 유니브 AP는 연결이 될 생각을 안 하네요. Okay. So intuitively, yeah. So when doing, I once did a group study with some of my earliest students for the Andrew Young's machine learning class, and there is a homework about this neural net. I mean, implementing this neural net, okay, by using MNIST. So if you did such kind of homework, and then you may have an idea. And then I just for just an interest, just for fun, I actually applied this TSNE or this dimension reduction algorithm for vector representation extracted from different layers, and then I obtained almost similar result. So we can actually do the if we just design this multi-layer neural nets, and then at each layer we can draw their own 2D scatter plots by using, for example, TSNE, and then you can easily see that the separation becomes more and more, clearer, okay, as we guess later layers. Okay, so so each layer in our neural net is it can be understood or it can be viewed as given really messy high-dimensional representation or multi-dimensional representation. Each layer is actually gradually processing or gradually transforming your data into another multi-dimensional vectors, but those multi-dimensional vectors are formed in a way that they are better separate, better classified or separated by using simple linear classifier, right? Because at the end, so if we do this multi-layer multi-layer neural net, and at the end, when doing the binary classification or the multi-class classification, at the last layer, it will always be the linear classifier, right? So if we achieve the high performance, and then it means just one layer before, okay, that layer is providing easily and also linearly separable vector representations of our data, right? So that way, this neural net is improving the vector representation of the same data gradually over layers, okay? So that it is better separated with respect to our given labels, okay? So that way, this neural net is also called representation learning. Okay, representation learning. It is learning the representations, for our own purpose. So if our purpose is to classify an image between the male and the female, and then given that label, once the training is done, and then each layer is gradually improving the separability of our data in our feature space, with respect to the given labels. Okay, so that way. It is just called the deep learning is often called the representation learning, and also if you think of your projects, and then there is one emerging conference called iClear. So have you guys heard about this conference name, ICLR? So there are the three major conferences within the machine learning and deep learning areas. Although there are many other neighboring kind of conferences focusing on a particular application, such as computer vision or natural language and speech and so on. But just purely focusing on deep learning itself or machine learning itself, there are 3 major conferences, which are iClear, and another one is NIPS, and so these are the major ones. And yeah, these 2 have been around for several decades, for at least 10 to 20 years, I think. But this iClear has started just maybe just 5 or 6 ago, or 5 years ago, or 6 or 7 years ago. So it is a really new kind of conference. But yeah, that became really quickly the most prestigious conference within this domain. But anyways, the reason why I'm introducing this is because this is the acronym for International Conference on Learning Representation. Okay, so learning representations is the key concept or key task in almost all the neural net or deep learning tasks. Okay, so back to this VGG case. So yeah, we can understand that having more chances or more opportunities to introduce nonlinearity will give us more kind of more opportunities to selectively squash some regions so that we can provide a better separability to the next layer. Okay. Okay, and also this VGGNet, although there are better alternatives, including Google, such as GoogleNet and ResNet, but due to its simplicity, VGGNet is also quite widely used still in these days. Okay, and you guys understand this, right? So the number of the size of an activation and the number of parameters. And I think we briefly discussed about it, right, by using some figures, right? So so in terms of an activation, this gets largest, and in terms of the number of parameters per layers, and this the first fully connected layer will have the largest number of parameters. So this inception module, although it's a naive one, this is the inception module, and let's look at the naive one first. So let's just understand it more carefully. So we can think of this one-by-one convolution. So at first, when studying this, it didn't make sense to me, because convolution is actually extracting out some spatial patterns, right? So the smallest possible filter size could be, it should be 3 by 3, right? Because that way, this is the smallest size involving multiple different pixels, so that we can define a particular pattern, whether it is like this or maybe like this, right? So in order to determine this particular spatial patterns, we don't actually, we cannot do this kind of job using a convolution filter using a single pixel, right? But still, this one-by-one convolution has the effect. So that effect is as follows. So okay, so let's think of a one-by-one conv here, and then let's first think of the filter size. So the filter size is 1 by 1, and what is the depth? Depth is 3 in this particular case, right? And then, this guy is placed over here to obtain the inner product output, right? and that way we obtain the single output over here, and then when moving that filters to the next position, and then we obtain another activation output, and that way we still have this 4x4 activation map, right? And then what is the characteristic of this value? So this value is actually a linear combination of these three different values. Okay, so if it has 3 channels, and each channel will have its own meaning. So for example, this guy is the how strongly a particular pattern exists in that particular position. And so the first channel is looking at the cat's eye, and the second channel is cat's eyebrow, and the third channel is cat's nose, for example. And then if we just combine those 3 informations, and then this single activation map can be representing some information like, okay, so it is activated, or it gets a high activation value when the cat's nose is found significantly, but cat's eyebrow is not found significantly, but also cat's nose is also found significantly. So that way we can kind of combine those informations, distributed or informations across different channels into a single value, right? So if we have another filter of 1x1 having 3 channels, and then it will have its own kind of linear combination weight. So for example, linear combination weight was 1, 2, and -1, and then maybe another linear combination weight will be 3 and -2 and 0. So different linear combinations that combines different channel activations at the input level. Okay, so that way we can have a different way of combining those different information. So that is the meaning of the 1x1 conv. Okay. So the time's up, and I think it's probably the last class before our midterm exam. Okay, but the exam scope will be based on the entire chapter 9. Okay, even though I wanted to give more explanations about this chapter, but we will continue after the exam. But still, the exam scope is up to this chapter 9. Okay. And also if you have any questions, and then you can post it in the Slido, and then I'll give an answer with my best at the KakaoTalk room.